Hi, Joyce.
Hi, Joyce. They're so excited to talk to you. So sad. She might.
Why did I do it? Why did I do it? I knew it was coming.
So 56, what's going on?
I don't really know.
There's a minus 1 inside the argument, but then there's also an absolute value. So the minus 1 would be a shift to the
Shift down. Go down 1.
Do you guys remember what an absolute value on the inside does to the graph?
No.
By the way, Joyce, in the back of the spirals, and they were doing this to begin class after reading their homework and going over questions. Let's just roll camp 56. The rest of them I think they got. And then the answers were, guys help me out real quick, 51? 0, 0, 52. 13 fourths?
Yeah.
53?
1 4.
54?
1 half.
Ooh, how'd you get that one? 55?
3/4.
Okay, so let's come back to 54, because you just put an absolute value in, right?
Yeah.
So what did you do that was different?
I kind of split it up. I did 2 different integrals. Integral from -1 to 0, and then 0 to 1.
True. But the reason why you can do that, you don't actually have to split it up, and that's why you guys, I heard you talking about, like, what have you really talked about that yet? Splitting it up and whatnot? F of x is equal to, let's just do an illustration. Let's say f of x is something like this. Okay, maybe the cube root of x or something like that. It's an inverse sum. The cube root of x. Okay, so we have f of x. What's going to change if we have a transformation f of absolute value of x?
Of x cubed?
Just absolute value. We're just plugging into whoever it is. Whatever's on the right stays the same, because positive x's are positive x's, right? The positives stay the same. What happens to all the negatives? But it's not that the y's become positive per se. It's that the negative x's will behave like the positive x's. So whatever was on this side is copied on the other. You guys don't like this. Let's do this illustration. But some of you might not get this, what I mean. So it has nothing to do with this. The negative x's used to have their own identity and get their own values. But now that the negative x's behave like the positive, whatever was going on the positive side is now going on the negative side. So, for this one up here, if I'm thinking between -1 and 1, what was going on between 0 and 1 is just going to be double. Okay? So then, when you think about, so we have a shift to the...
Shift down.
Not down. To the right.
Wait, where?
Why? Because it's inside your x cubed, so it's a horizontal shift, right one?
Oh, that one.
Remember x minus 8.
What graph gave me this? Gave me one down.
Went down one. You had it in parentheses with cube?
Yeah. Maybe I did it wrong.
Actually, you know what? What you might be seeing, you think it's down one, but it's the right one. Because x cubed ends up going like this, right? Normal x cubed. And then when we have right one, what's going to end up happening? Right?
Yeah.
And then when we have absolute value of x minus 1, right?
Yeah,
Oh, so it looks like it's down.
Yeah, so it looks like it's down one, right? So that makes sense, but it's really right one. And whatever's on the right is going to be mimicked on the left, and so then when I have my right one, so my 0 to 1 got shifted to 1 to 2, right? Is that right? My 0 to 1 got shifted 1 to 2. Oh, trouble.
But the
My 0 to 1 got shifted 1 to 2. Which would be the same thing as what's going on the other side from -1.
Steve, can you say that since it's not only on the outside of the absolute value,
This is 1/4, yeah?
but it's also on the inside of the cube. You can say it moves right and down at the same time.
No, that's not 1/4.
You can't say it's right and down at the same time.
Steve, that's not 1/4.
Wasn't that the region that was in between 0 to 1 originally though?
Yeah, but 0 to 1 is like the change of no point of inflection to the.
Right, this is the point of inflection. See?
Okay.
Right, see, was my point of inflection, I just shifted him over.
So what is it?
So that's 1/4, and
That's
so then
1
we
to
have.
2? Is that 1 to 2?
Maybe 1 and 2. That's 1 and 2. I'm not sure how to even solve that actually.
Wait.
If
Wouldn't
one
it
was
be-
above and one was below, we could cancel them out.
Wait a minute. Can't you think that the original function would be going down, so it would be 1/4? But since you flipped it, it would be like half of that, so it would be like 1/8. Since you flip it up, that region becomes 1/8.
Oh, because of symmetry. Okay, that makes sense.
I'm just confused on why that's 1/4. Isn't it moved? It's moved 1.
So what was between 0 and
1.
1? See, my perspective is a little messed up. Zero, zero, 1, 1. This is what you had before, right? Between 0 and 1? He's 1/4. And we shift him to the right, 1. This point is now, this point is now. An absolute value.
Yeah.
So then, from 1 to 2 is the exact same area. That's what I was trying to show. Does that make sense? But then we also have this area, and then this area. Okay, that makes more sense. Now I'm tracking.
Wouldn't that be
So it's
0?
gonna be negative 1/4. Yeah?
Negative.
Negative.
Yeah,
Because
I
of
know it's
symmetry, I
negative,
wasn't thinking of symmetry. So what's above is gonna be below, so these two are gonna cancel, but I have to go all the way back to negative 1. Right? So it's gonna be negative 1/4. Let me double check real fast. Negative 1/4.
Oh, with this. Oh yeah.
Write that down.
So my lame graphical representation that was not precise messed this up. Okay, here we go. 6-3. All those properties, you were like, wait a minute, have we talked about them yet? Now we are. Plus a couple extra. Plus a couple extra.
You gotta go fast.
Definite intervals and antiderivatives. So, Gerardo, we are introducing the idea of antiderivatives in context of definite intervals today. However, we're going to focus more on them tomorrow in section 6.4. So, fundamental theorem of calculus technically is 6.4. You can do all the implications, applications of that.
Do we have to know these ones?
Not necessarily.
Do we have to write any of them down?
Oh, the 6 and
What are the new ones?
6 and 7?
Zero additivity, order of integration, constant multiple, sum and difference, 6 and 7. 6 and 7 are the only new ones. But as you guys are thinking through, or as you guys are writing, why is the integral from a to a equal to 0? It hasn't moved. And if you think of an integral as an accumulation of area, which is what those accumulation problems yesterday were trying to reinforce in your mind. If an integral is just an accumulation, like you keep on moving through different x values, looking at the heights, the infinite sum of the infinitesimally small subintervals, or the area in those infinitesimally small subintervals, then yeah, from a to a, you haven't gone anywhere, so the area is 0. Additivity just says, as you go from one lower bound to another upper bound, and that one's lower bound to another upper bound, you're just accumulating those two, so you're adding those two areas together, just like we could do in geometry, etc. Order of integration, we're actually going to talk about just for a quick second. Because the book, there's a cool illustration as to why that is what it is. Besides thinking forwards and backwards, going forwards on a graph, above is positive, below is negative. Going backwards on a graph, everything is backwards, above is negative, below is positive. Constant multiple, what else you can pull out? Sum and difference. In integrands, you can split up the integrands to be two separate integrals of the separate functions. But 6 and 7, a little interesting. I haven't seen the AP specifically test on it, but if you do know the idea of it, and you were stuck on an integral, you could technically at least see what it was supposed to be in between. The lowest it could be and the highest it could be, and it might be able to help you narrow down some options, so it's kind of interesting. So the maximum inequality says, all right, fine. Area. When we're talking about area under a curve, I'm just going to do a representative one real quick for number 6. We're talking about area under a curve, per se. And here's our f of x. And we'll say, here's our a. And we'll say, here's our b. Right? We can see the area. My question, though, is what is the minimum value of f? We could find that, right? And the minimum would be over here somewhere? Over here somewhere? And they say, okay, make that your height. So the min of f would be at some little, like, c. And then say, it says multiply base, or b minus a to be your base, and then f of c to be your height. And then it's like, hey, that's the minimum. That's the lowest the area could possibly be. It's going to have to be something higher than that. So we can say in this context, for the minimum, in our graph, we could say that would be f of c times b minus a. And then we find the maximum value in this interval, which would technically be at the endpoint, yeah?
Yep.
And then if I made b minus a be the length of that, and have f of, in this case it would be b, that's the maximum area that I should have. So then the maximum would be f of b, in our example, times b minus a. And the idea is that integral has to be somewhere in between. Which logically, graphically, probably makes sense, but it's something that we never really pulled out before, something we've never really visualized before. But it does have to be somewhere in between that lowest rectangle and that highest rectangle that could fit inside the region. And I don't mean smallest rectangle, because that would be an area of 0, but I mean the rectangle at the minimum and the rectangle at the maximum. So I thought that was interesting.
And this one.
And then the domination just has a cool name, right?
Well, it helps out with the number, whatever on homework. Like with proving that if the graph is positive, then the interval is positive.
Yeah, so that would help with the domination property. So you're kind of leading up to this one, the domination property. If a function is always higher than g, and this is sounding like the AP guys, right? If the function is always higher than g, then his area has to be higher, greater than or equal to g as well. So if all of his y values are always greater than or equal to g, then of course his area is going to be greater than or equal to g. And then if a function is always positive, well then his area is always going to be positive as well. And we could say the same thing about negative, right? If the function is always negative, his area is always going to be less than or equal to 0 as well. Okay, so with that, are we okay-ish? No. What if I was to give you the following? But why is it 0?
Because the second one is the negative of the other.
If we go from A to B, and then we go from B back to A, question, what is our total displacement?
0.
So we can say it's the exact same thing as from A to B and B to A. It's the exact same thing as the integral from A to A of f of x dx. So we can say that the integral from A to B of f of x dx, if that's just 0, which you guys already said, look, it's the reason why our property is what it is. You go from A to B and then back to A, well then your displacement is 0, so your total area is 0, so then you can say, oh, well therefore A to B must be the opposite of B to A. And that's why we can say things like if you're going backwards, it's going to be opposite what you think. The examples, hey, it looks kind of similar to what we did to start class, but now we technically have all those properties that we can use and implement. So let's go a lot faster, hopefully. Yeah.
I get to ask this. is that like stuff we just need to like just focus on a graph and just kind of look at the graph?
It's visualizing total change graphically with the graph of budget or very or constant.
Some of it we can do up here, but others we have to actually draw it out.
It depends on, if you look at square root of r squared minus x squared, goes to circle, like you just look at the bounds to know whether it's a half circle or a full circle, etc. So you don't have to always draw it out.
Because like the last one we have to draw it out.
Oh, true. And letter A, from 2 to 2? That's easy. Letter B, from 1 to, from 5 to 1.
Negative.
Yeah, take the 1 to 5 and just make it negative 8. Yeah. For C, from 1 to 2 of 3 aspects?
Negative.
Yeah, we just go ahead and multiply 3, no big deal. And then from 2 to 5 of f of x? What do you think?
Isn't it so fast?
What we could do is you can take the negative of the first one and add it to the second one.
Or you can just do 1 to 2 and then subtract that.
1 to 5 and then minus 1 to 2?
That's what we mean.
Yeah, you can do 1 to 5 minus 1 to 2, which would be the same thing as 2 to 1 and then 1 to 5, which
Yeah.
is technically using the property. And 2 to 1 would be the opposite, which would be the negative. So the negative and negative 4 and then 6? 7. And then it's the difference property says, oh, no big deal. If you have 2 separate ones, who cares? Just take the 6 and then subtract the, so then negative 2. And then 4 times f of x from 1 to 5. Line it up. That'd be just 4 times 6 is 24 minus 8 is
16.
So close.
16. Now, where or how does number 8 get interesting?
I'm gonna prove it. Oh, is this linearization?
No, actually not linearization. Wait a minute.
So are we
It
doing
tells
max
us where it
and
lies between max and min, right? So you can do the max and min. The max and min of what? Wait, what are we doing?
F of x, which is x plus 8.
Uh-huh. So we want to figure out the min
So we're going to divide it.
and the max. We could derive it, or we could say like, wait a minute, isn't this a function? I kind of know what he looks like. Isn't he a square root? But he's over here at negative 8. And isn't he strictly increasing? That kind of makes sense. He's a square root function. Nothing weird is going on. Square root of x plus 8, so he's just been horizontally shifted left 8. So if he's strictly increasing, where is the minimum going to occur? And where's the maximum going to occur? On the interval 0.
So the min is going to be negative 8. Or well, f of
Well, thinking about the bounds though.
0. That'd be 2 root 2.
So the min is going to be the first point, right? 'Cause that's the lowest if it's strictly increasing. And the max is going to be at the last point, right? 'Cause that's going to be the highest it goes. So then can't we just go ahead and say, oh, okay, well, hold on.
And then just f of
F of, exactly. F of 0 times 1 minus 0. And then f of 1 times 1 minus 0. Plugging in 0, we just end up with square root of 8 times 1 square root of 8, which is really just 2 root 2. And then f of 1 is going to be square root of 9, which is just 3 times 1. So we can say by the max and min property, basically. That, yeah, an integral is going to have to be in between. Right? Just illustrating. I think it's a kind of nifty one. Because if you get to one of those problems where, especially when we get to harder integrals, if it is one of those that you're totally stuck and you just totally don't remember what to do and you don't have a calculator, this could be one way of at least approximating, right?
or like excluding.
Yeah, exactly. Like narrowing down to have a better percentage of getting there. Okay, average value. Ooh, 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 ooh. At the bottom of the page is the formula for the average value of a function f over an interval a to b. However, you don't necessarily have to write this paragraph. I just want to show you an idea because I thought it was pretty cool. But first, how do we average things? Jordan, we were talking about this yesterday, right? Or 2 days ago? Which would have been Friday. Take the sum of all the values
Divided by
and divide by how many. But what's the struggle if I'm taking or finding the average of a function that I have over an interval a to b. How many values are there in between a and b? Infinitely many. So how can I sum infinitely many and divide by infinitely many points? Yeah, basically with the limit. But if we were to go ahead and section off or split a function into, or I should say, split the a to b into different subintervals, and I pick in each of those separate subintervals a constant, a c. And yeah, I could say limit as n goes to infinity, so I have more and more subintervals, so I have more and more c's, and as a result, I'm accumulating more and more values that I'm averaging. I could technically take these different values, add them all up, put them in a summation, and say, okay, 1 over n, but then it's like, well, that doesn't match anything that we know. But if we were to think about this formula, we could go ahead and say that n is equal to b minus a all over delta x. Then I could go ahead and plug in and say, well, 1 over n is going to be delta x all over b minus a equals 1 to n of f of c to the k. And if I realize that delta x for any given scenario is going to be a constant, I can actually move him, in a sense, in. I can put a 1 on top. And I can take a limit as n goes to infinity and question, kiddos, what do you see going on right here?
An integral.
That's an integral. With an additional what?
Represent. Constant. Whatever you want to call it.
1 over b minus a.
You just multiply.
So in essence, by integrating a to b of f of x dx, you are accumulating the total change, or you're accumulating all the different function values, I should say. And then you're dividing by b minus a is going to give you, in a sense, the range of numbers that you need to find the average. Now with units, it makes a little bit more sense, and we can actually apply it, and we can say, hey, if we integrate miles per hour, we get miles, and we divide by hours, and we're like, hey, yeah, it's the average miles per hour. But without units, I thought this was a kind of cool illustration to show what's going on. However, we need to practice average value just a little bit, and to do so, I thought, why not? Let's go look at.
Oh, you again.
Why?
Just know because it was so easy.
It was so easy, letter A. All you had to do to find the average value of the radius of the funnel is say, who is the radius of the funnel? 1 over 20 times 3 plus h squared. And from the formula that you just saw, how do you find average value of somebody that you already have? And for the situation that we're given, it's between 0 and 10. However, common mistake, some people forgot to keep going and do what? 1 over 10. Oh my goodness, this is super hard though. How on earth are we supposed to solve?
Is this a calculator?
No, it's question number 5, not a calculator problem.
The first
FTC. You just do FTC. Wait, how do you do FTC? You know how to find antiderivatives. Oh, let's go back to the section. But does it make sense why we use the formula?
Yes.
We have radius. They want the average of the radius. They want the average of what we have. So this formula, when I say, that's not what I want to do, go back. To find the average of a function that I already have, I want the average radius, in our case, the average of f, we plug it into an integral. Average rate, we take a not derivative, we take a slope. But average value of something that we already have, we take an integral. We'll go back to him once like tomorrow we'll come back. So, antiderivatives. Arbo takes an interesting take on it, but it's one that we'll be able to use. It technically starts with the mean value theorem for definite integration. Last year, mean value theorem, we said that this was the theorem that said, hey, there exists a perfect rectangle within a to b at a given function value of f that is the exact area, because the alternate form is, you could think of it as f of c times b minus a, which I hope with some of the work that we've been doing, you guys are kind of seeing that as an area formula a little bit better than even last year. F of c times b minus a is the height times the base. A couple different ways of writing the mean value theorem, but saying as long as the function is continuous at some point c in a to b, there's going to be a perfect rectangle such that. That's one way of looking at it, but with the other form of writing it, we could technically say there's going to be a value that equals the average value of f. And that makes a little more sense as to why it's called the mean value theorem, because mean is another word for average. So the average value of f, there's going to be some place, some particular x equals c within a to b such that the function value at c is the same thing as the average value. So anyway, that kind of connects a little bit better with the mean value theorem. We're not using it a lot, the mean value theorem in homework or in section 6.3 specifically. They use it to introduce because it's needed for the next proof that they give for what an antiderivative is and does. Technically, last year we called this FTC Part 2. Some people call this FTC Part 1, and the other one that we talked about is FTC Part 2, which is a bit of a bummer. So we just kind of say FTC and just hope that people know what we're talking about. However, if an antiderivative, and people from last year, what letter do we usually call an antiderivative? If capital F is an antiderivative of little f. And if I know the derivative of an integral in a sense undoes each other, which kind of shows us the idea of an antiderivative. Because you take the derivative of an integral, they're inverses of each other, so one is the anti of the other. Then I can say, in some senses, that the integral from a to x of f of t dt is equal to the antiderivative f of x, and then we usually tack on a little plus c, right? So an integral by itself is going to underive, or we say antiderive. So you have to look at the integrand as a function, as you guys all know, as the derivative answer we're trying to go backwards. Now, without going into all these different formulas per se today, let's just take a few. The better way that I like to say it, rather than the book describing how, like, hey, a derivative and an integral are inverses of each other, is to say that capital F prime is little f. And so we look at our little f. Hold on, pause. How do you solve antiderivatives? Or sorry, how do you solve definite integrals?
How do you solve definite integrals? You have to take the antiderivative and then plug in the back.
You say, hey, you're the derivative of somebody's, and who are you the derivative of?
E of x.
Literally, yeah, e to the x. We write a little from 0 to 1 to say, hey, we need to change it, and we'll see tomorrow in section 6.4 with that formula. But we can say e to the 1 minus e to the 0, f of b minus f of a. So we end up with e minus 1 as our final answer. So come back over here with definite integrals from a to b. That's our quick little reminder. And I can show you tomorrow as to why our book decides to introduce this now and not in the next section. But that is how we solve the definite integral. Sound good? Yeah, don't worry. We're going to talk about fundamental theorems tomorrow, and that's the one that I tried the better reason. But they did have an interesting reason as to why they introduced it. Alright, you guys good? We're doing tomorrow. Oh yeah, 6.3. It's not going to be bad.
Up to
All of it, because it's not. It's not bad. So you're using properties and then you're solving for some antiderivatives.
I got bored and I just thought it was gone.
It's called properties.